When dealing with single-phase loads connected to a three-phase panel, it's crucial to understand how to correctly calculate the amperage for panel schedule entries. The confusion often arises when trying to adapt single-phase power calculations to a three-phase system. Let's clarify the correct method, particularly for 208 volts and 480 volts single-phase loads. The key principle is to always use the actual voltage that the load is designed to operate at when calculating the current. In the example given, a 2228 watts load is connected to a 208 volt single-phase circuit. The correct way to calculate the amperage is to divide the wattage by the voltage. Therefore, 2228 watts divided by 208 volts equals 10.7 amps. This means the load draws 10.7 amps from the 208 volt source. The reasoning behind this is based on Ohm's law and the power formula. Ohm's law states that voltage equals current times resistance, or volts equals amps times ohms. The power formula states that power equals voltage times current, or watts equals volts times amps. When you know the power and the voltage, you can rearrange the power formula to solve for the current. Amps equals watts divided by volts. Applying this to the given example, you use the actual voltage, 208 volts, because that's the potential difference driving the current through the load. Dividing the wattage by 120 volts and then dividing the result by 2 is incorrect. This approach misunderstands the voltage relationship in a three-phase system. While it's true that in a 208 volt system, the voltage from phase to neutral is approximately 120 volts, the load isn't connected between a phase and neutral. It's connected between two phases, resulting in a 208 volts potential difference. Using 120 volts in the calculation would be relevant only if the load were directly connected to a 120 volt circuit. To illustrate this further, consider a scenario where you have a 480 volt single-phase load on a three-phase panel. Suppose the load consumes 4,800 watts. To find the amperage, you would divide 4,800 watts by 480 volts, which equals 10 amps. Again, you use the actual voltage at which the load operates. A common mistake is to confuse line-to-neutral voltage with line-to-line voltage. In a three-phase system, the line-to-line voltage is the voltage between any two phases, while the line-to-neutral voltage is the voltage between one phase and the neutral conductor. For a 208 volt system, the line-to-line voltage is 208 volts, and the line-to-neutral voltage is approximately 120 volts. For a 480 volt system, the line-to-line voltage is 480 volts, and the line-to-neutral voltage is approximately 277 volts. Always identify how the load is connected. If it's connected between two phases, use the line-to-line voltage. If it's connected between a phase and neutral, use the line-to-neutral voltage. When entering these values into a panel schedule, you would list the calculated amperage, 10.7 amps in the 208 volts example, and the two phases that feed the circuit breaker. The breaker would be a two-pole breaker because it's connected to two phases. For the 480 volts example, you would list 10 amps and the two phases feeding the corresponding two-pole breaker. Let's consider a more complex example. Imagine you have several single-phase loads connected to a three-phase panel. One load is 1500 watts at 120 volts, another is 2000 watts at 208 volts, and a third is 3000 watts at 480 volts. Firstly, for the 1500 watts at 120 volts load, the amperage is 1500 watts divided by 120 volts, which equals 12.5 amps. This load would be connected to a single pole breaker between one phase and the neutral. Secondly, for the 2000 watts at 208 volts load, the amperage is 2000 watts divided by 208 volts, which equals approximately 9.62 amps. This load would be connected to a two-pole breaker between two phases. Thirdly, for the 3000 watts at 480 volts load, the amperage is 3000 watts divided by 480 volts, which equals 6.25 amps. This load would also be connected to a two-pole breaker between two phases. When filling out the panel schedule, ensure you allocate the correct amperage to the corresponding phases. For the 120 volts load, the 12.5 amps would be listed on one phase. For the 208 volts load, the 9.62 amps would be listed in the two phases connected to the breaker. For the 480 volts load, the 6.25 amps would be listed in the two phases connected to its breaker. Accurately calculating these values is crucial for several reasons. Firstly, it ensures that the panel is properly loaded, preventing overloads which can lead to breaker trips and potential damage to equipment. Secondly, it helps in selecting the correct size of conductors and overcurrent protection devices as required by the National Electrical Code, or NEC. Thirdly, it provides an accurate representation of the electrical system's load profile, which is essential for efficient energy management and future planning. Understanding the relationship between voltage, current, and power in both single-phase and three-phase systems is fundamental to electrical engineering. When you encounter a situation where you need to calculate the amperage of a single-phase load on a three-phase panel, remember to always use the actual voltage that the load is designed to operate at. Avoid the temptation to divide by a different voltage or apply arbitrary factors. In summary, the steps for calculating single-phase load amperage on three-phase panels are straightforward. Firstly, identify the voltage at which the load is designed to operate, either 120 volts, 208 volts, 480 volts, or another voltage. Secondly, use the power formula amps equals watts divided by volts to calculate the amperage. Thirdly, enter the calculated amperage on the appropriate phase or phases in the panel schedule, depending on whether the load is connected line to neutral or line to line. By following these steps, you can ensure accurate and safe electrical system design and operation. Now let's delve into how this relates to the NEC, specifically regarding conductor sizing and overcurrent protection. The NEC provides guidelines for selecting the appropriate size of conductors and overcurrent protection devices such as circuit breakers or fuses based on the calculated load current. Section 310.15 of the NEC covers ampacity, which is the current carrying capacity of conductors. When determining the minimum size of conductors for a circuit, you must ensure that the conductor's ampacity is not less than the calculated load current. For example, if you have a 208 volt single-phase load that draws 15 amps, you would need to select a conductor with an ampacity of at least 15 amps. The NEC provides tables such as Table 310.16 that list the ampacities of various conductor sizes based on their insulation type and installation conditions. Additionally, the NEC requires that overcurrent protection devices be selected to protect conductors against overloads and short circuits. Section 240.4 of the NEC provides guidelines for overcurrent protection. The general rule is that the overcurrent protection device should be sized to protect the conductor in accordance with its ampacity. However, there are exceptions to this rule, such as when dealing with small conductors or specific types of equipment. For instance, if you have a 14 American wire gauge, or AUG, copper conductor with a typical ampacity of 15 amps, you would generally use a 15 amp circuit breaker to protect it. However, for certain motor circuits or equipment circuits, the NEC may allow for a larger overcurrent protection device to accommodate inrush currents or other specific requirements. Another important aspect to consider is voltage drop. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and no more than 5% for feeders. To calculate voltage drop, you need to know the conductor's resistance, the length of the circuit, and the load current. There are various online calculators and software tools available to assist with voltage drop calculations. Furthermore, when working with three-phase systems, it's essential to ensure balanced loading across the phases. Unbalanced loading can lead to increased neutral currents, voltage imbalances, and potential equipment problems. To minimize unbalanced loading, try to distribute single-phase loads evenly across the three phases. For example, if you have several 120 volt circuits, connect approximately 1/3 of them to each phase. In addition to the NEC, local codes and regulations may also apply to electrical installations. It's crucial to be familiar with these requirements and ensure compliance. Local codes may have stricter rules or additional requirements beyond what is specified in the NEC. Moreover, proper grounding and bonding are essential for electrical safety. Grounding provides a low impedance path for fault currents to return to the source, allowing overcurrent protection devices to trip and clear the fault. Bonding ensures that all metal parts of the electrical system are electrically connected, minimizing the risk of electric shock. The NEC provides detailed requirements for grounding and bonding in Article 250. In conclusion, accurately calculating single-phase load amperage on three-phase panels is a fundamental skill for electrical engineers and designers. By understanding the principles of voltage, current, and power, and by following the guidelines provided in the NEC and local codes, you can ensure safe and efficient electrical system design and operation. Remember to always use the actual voltage at which the load is designed to operate when calculating the amperage, and consider factors such as conductor sizing, overcurrent protection, voltage drop, and balance loading. Now let's discuss some practical applications of these calculations in real-world scenarios. Consider a commercial building with a three-phase 480 volts electrical system. The building has various single-phase loads, including lighting, receptacles, and small appliances. To design the electrical system, the engineer must first determine the total load for each area of the building. This involves calculating the amperage of each single-phase load and adding them together. For lighting circuits, the engineer would calculate the amperage based on the total wattage of the luminaires and the voltage of the circuit, typically 120 volts or 277 volts. For receptacle circuits, the engineer would use the NEC guidelines for calculating receptacle loads, which are based on the area of the space and the type of occupancy. For small appliances, the engineer would calculate the amperage based on the nameplate rating of the appliances and the voltage of the circuit, typically 120 volts or 208 volts. Once the total load for each area is determined, the engineer can then size the conductors and overcurrent protection devices for the branch circuits and feeders. The engineer would also need to consider voltage drop and ensure that the voltage at the load is within acceptable limits. In addition, the engineer would need to balance the loads across the three phases to minimize neutral currents and voltage imbalances. Another practical application is in industrial facilities with large motors and equipment. Industrial facilities often have a mix of single-phase and three-phase loads. To design the electrical system, the engineer must accurately calculate the amperage of each load and consider the starting current of motors, which can be several times higher than the running current. The engineer would also need to coordinate the overcurrent protection devices to ensure that faults are cleared quickly and safely. Furthermore, in renewable energy systems such as solar photovoltaic or PV systems, accurate load calculations are essential for designing the inverter and the grid interconnection. The inverter converts the direct current, or DC, power from the solar panels into alternating current, or AC power that can be used by the building or fed back into the grid. The engineer must calculate the total AC load to ensure that the inverter is sized correctly and that the grid interconnection is capable of handling the power generated by the solar panels. In summary, accurate load calculations are critical for a wide range of electrical engineering applications. Whether it's designing the electrical system for a commercial building, an industrial facility, or a renewable energy system, the ability to correctly calculate single-phase load amperage on three-phase panels is essential for ensuring safe, efficient, and reliable operation.